The analog to digital converter, or ADC, is a circuit that takes an analog voltage and converts it to a digital number. Most modern PIC and AVR microcontrollers contain some type of integrated ADC, with features varying depending on the product family. This video will focus on the new Adccc with context switching, or analog to digital converter with computation and context. Adccc with context switching is an improved version of the ADC that adds the ability to perform context switching and automatic channel sequencing. Without this feature, the CPU would have to stop the ADC, load the new settings, and then restart the ADC for each context. This has two main disadvantages. One is the delay caused by reconfiguration, and the other is a higher software complexity. With context switching, the ADC gains the ability to switch its settings without CPU involvement. The full list of switching registers are defined in the device datasheet, which is linked below. Some examples of registers that switch include the sampling channel, ADC computation mode, conversion time, pre-charge time, and conversion results. In the PIC18Q84, there are 4 sets of context duplicated registers available on the device. Another new feature is the channel sequencer. The channel sequencer is responsible for automatically triggering the switch to the next context enabled. Disabled contexts are skipped by the channel sequencer. When the channel sequencer is inactive, the channel context selection bits can be used to manually select a context to read or write. When the channel sequencer is active, the channel context selection bits are read-only. However, direct memory access, or DMA, can be used to access the context settings. However, it is strongly recommended to use the ADC status bits to ensure the ADC is not in the middle of a conversion before modifying a register in the contexts. In practice, the Adccc with context switching is most applicable for sampling multiple analog sensors where each sensor has its own context. For more information about sampling analog sensors in general, please check out the application note in the video description. In this example, 4 sensors are used to demonstrate the advantage of the Adccc with context switching: a thermistor-based thermometer, a gas sensor, a humidity sensor, and the voltage of a battery. Each sensor has differing measurement requirements. While the fixed voltage reference, or FVR, has only a single output for the ADC, each context can choose which reference to use: the FVR, power supply for the device, or an external reference. The thermistor changes its resistance in response to temperature. In this setup, the thermistor forms a voltage divider. The equivalent impedance of the sensor, which can be found by using Thevenin's theorem, is added to the impedance of the ADC to calculate the maximum time to acquire the signal. There are many types of gas sensors on the market. This will focus on a voltage output sensor. In this example, the output of the sensor is buffered, reducing the impedance of the sensor signal. While the acquisition time of the thermistor would work, it would be overly excessive. Instead, the acquisition time of this sensor would be primarily dictated by the internal resistances on the device, which are described in detail in the datasheet. Some humidity sensors have a capacitive output, which relates a change in capacitance to the humidity in the air. To measure the capacitance of the sensor, the capacitive voltage divider, or CVD, feature of the ADC is used. You can learn more about how the CVD works in the video description. The last item to measure in this application is the battery. The sensed battery voltage must be less than the reference used by the ADC. The simplest way to achieve this is to use a voltage divider. To maximize resolution, the peak battery voltage should be as close as possible to the reference level used. Like the thermistor example, the equivalent impedance of the divided signal must be found to determine the required acquisition time. The larger the impedances are, the lower the power loss of the battery is. However, this increases the required acquisition time and the noise of the circuit. Setting the ADC to one of the averaging modes may improve the signal-to-noise ratio of the circuit. Direct measurement of the battery is also possible, but only in the case where the microcontroller and the ADC reference voltage are above the peak voltage of the battery. In this case, a boost converter is used to supply the microcontroller with 5 volts while the battery is at a nominal 3 volt output. The internal ADC reference could be set to VDD or to the internal FVR level depending on the setup of the other channels. An approximation of the impedance inside the battery can be found from the discharge curve in the battery datasheet. The acquisition time will depend on the battery impedance plus the impedance of the ADC internally. The Adccc with context switching is a huge improvement in the efficiency of applications that sample multiple analog signals. Context reduces software complexity by simplifying the process for loading new settings, which also lowers the configuration time required. Channel sequencing complements with the context by switching to the next context independently of the CPU, which further improves the efficiency of the microcontroller. Thank you for watching. If you'd like to learn more about the Adccc with context switching or the PIC18Q84 family of microcontrollers, please see the links in the video description.